So let's look at integration in cylindrical coordinates. In cylindrical coordinates, we find that a triple integral over some volume can be converted into polar coordinates in the x and y coordinates, and then we leave our z coordinates the same. This notation looks a little bulky. Really, it's just what you think it should be. That we have bounds on z, we have bounds on r, and we have bounds on theta. We need to make sure that we have constant bounds on the outside, and each of the subsequent inner bounds needs to be fewer and fewer functions of the variables. Our function, we're plugging in r cosine theta for x, r sine of theta for y, because that's our conversion to cylindrical coordinates. Just like with polar coordinates, we're going to add in this r coefficient for theoretical reasons that I waved my hands at earlier that you can investigate more. So let's go ahead and just see an example. Let's say that I am wanting to integrate the function x squared plus y squared dA over some volume W. Only in this case, our volume W is given by a cone. Let's say our cone has height 2, and let's say that it's given by the equation z equals the square root of x squared plus y squared. That's this side of the cone. So if I wanted to, I could think about writing this in my xy coordinates. It turns out that that's going to be very messy. So instead of doing that, I'm going to show how to set this up so that we define it in cylindrical coordinates instead. So in cylindrical coordinates, remember, I'm thinking of my xy plane in terms of polar coordinates, in terms of r's and z's. So here's my xy plane. And in this case, the shadow that my volume makes in the xy plane is just a circle of radius 2. Shadow. So when I'm thinking of my region of integration, this is the same thing that we did before. Maybe I'll write it down here. This is my region of integration. So the base, which is the region of integration, is the circle of radius 2 in the xy plane. And so we're going to represent that in polar coordinates. It just means that my theta value is sweeping out in a full circle, meaning that 0 is less than or equal, I should write this in black so you can actually read it maybe. 0 is less than or equal to theta is less than or equal to 2 pi. We want to go in a full circle in this xy plane. And we know that our radius is as small as can be all the way out until my radius hits 2. So 0 is less than or equal to r is less than or equal to 2. Those are the bounds for the base of this region. What about the height? The height in this case, I'll do the height in green. The height is going to be given by the z values. We don't have to change the z values at all. And so we know that the maximum value for these z values are when z hits 2, because that's where we're cutting off this cone at z equals 2. And the lower bound is given by the formula for this cone. And in this case, I could write the top and bottom. So in this case, the top is given by z equals 2, whereas the bottom is given by z equals the square root of x squared plus y squared. We don't actually want to use x's and y's in our bounds on z, though. We want to make sure that we convert this into polar coordinates. I can do this algebraically if I wanted to, and I could see that, oh, this would be the square root of r squared cosine squared theta plus r squared sine squared theta, which ends up being the square root of r squared, which is just equal to r. And I could have seen that maybe originally algebraically. It just means that along this bottom part of the cone, no matter how far I go out in radius, that's exactly my height. I have a one-to-one relationship with radius and height. So that's another way to visualize this relationship. This tells me that my bounds on z in this case are going to be bounded below by the cone shape, which we just found was r. So r is less than or equal to z is less than or equal to 2. Notice that these bounds of integration, they're pretty nice. It means that it'll be pretty nice to be able to set up our integral. So we have these bounds. I'll write them down. I want to make sure I write them in the right order. I'm going to start with theta on the outside and then go to r. These are both constants, so it's not going to matter what order they go in, other than the fact that we need constant terms on the outside. So theta is going from 0 to 2 pi. R is going from 0 to 2. Z is going from r to 2. And my function in this case is x squared plus y squared. I'm going to convert that function into polar coordinates. So x becomes r cosine theta squared plus r sine theta all squared. This is our function. We can't forget our red r. Our red r tells us that it should be r dz dr d theta. And the rest of this is just easy. Now we just compute it. So how do we go about computing this? I might simplify the interior of this function. Just to save pen, I'm going to leave that as a triple integral without filling in all the details. The cosine squared plus sine squared becomes 1. So this interior just is r squared. R squared times r becomes r cubed. dz dr d theta. So let's integrate with respect to z first. I'm treating r cubed as a constant, and I end up with zr cubed evaluated from z equals r to z equals 2. So when I plug in z equals 2, I get 2r cubed minus when z equals r, I get r to the 4th dr d theta. I integrate this with respect to r, and I get 2 divided by 4, which is 1/2 r to the 4th minus 1/5 r to the 5th, evaluated from r equals 0 to 2 d theta. Finishing up over here, when I plug in 2 for r, I get 2, 4, 8, 16 halves, which is just 8, minus 32 fifths. When I plug in r equals 0, I get 0. So I evaluate this integral. The r's are all gone with respect to theta, as theta goes from 0 to 2 pi. So this is just one big constant. Integrating with respect to theta, I get 8 minus 32 fifths times theta, evaluated as theta goes from 0 to 2 pi. When theta equals 0, this whole thing is 0. So I get 2 pi times this stuff. 8 times 32 fifths, or 8 minus 32 fifths times 2 pi. I'll leave this as my final answer. Obviously, I could simplify the fractions a little bit. But this is just integration work. The hard part is setting up the bounds. What was the base of this figure, and how did the heights vary? So let's take a look at an example of computing a triple integral using spherical coordinates. So let's say my volume W in this case is given by a portion of a sphere. I only want the top portion of the sphere of radius 2 that's in this positive xyz octant. That's actually the first octant of our multidimensional coordinate system. And let's say that I'm integrating over the function x squared plus y squared plus z squared. So how do I go about doing this? My first step is I'm going to convert the bounds of integration into spherical coordinates. I know that this is a good call because this is part of a sphere, and in general it's going to be easy to convert parts of spheres into spherical coordinates. So let's do it one coordinate at a time. In this case, my rho value, just looking at this picture, I see that I want to include all of the volume that starts at the origin and goes all the way out until my radius is equal to 2. And because it's a sphere, I know that my radius is equal to 2 in every direction. So my rho is going to go from 0 to 2. Let's think about our theta. Theta values are tracing out the angle that I'm making with the x-axis. And we see that our angle starts at 0, and we're going to go around in a circle until I hit the next y-axis. And so I've only traveled a quarter of a circle, which is a pi over 2 amount of travel. So in this case, theta is going to go from 0 to pi over 2. If I had traveled in a whole half circle, that would be theta going from 0 to pi, but I don't want to travel the whole half circle. Finally, for my phi values, that's the angle that I'm making with the z-axis, that I want to have an angle of 0 with the z-axis, because we're starting all the way here at the top, and we're going to trace downwards until we get flat, horizontally flat, and that's where our phi value stops, meaning that our phi values are also trapped between 0 and pi over 2. That's the hardest part, is the visual interpretation of what my region looks like. Sometimes you have to do algebraic computation as well. That's something I'll leave for you to do in your homework. But it means that we're almost done. Now, our next step is I have to convert this inside formula into rhos, phis, and thetas. And I can do this, I'll do it algebraically the long way once, and you'll say, oh, I don't really like doing it algebraically ever again. One, I can recognize by definition the fact that x squared plus y squared plus z squared, the square root of this is a distance function, meaning that this really should be just rho squared. But let's go ahead and do the computation. I can plug in the fact that rho sine of phi cosine theta is equal to x, and that's squared, plus rho sine phi sine theta squared, that's equal to y, plus rho cosine phi squared is equal to z. Immediately, I'm going to pull out a rho squared from each of these terms, because the rho squared is redundant. And I see that I'm left with sine squared phi cosine squared theta plus sine squared phi sine squared theta plus cosine squared phi. So again, I'm going to pull out a sine squared phi from these first two terms. So I have a rho squared on the outside. I have a sine squared phi times cosine squared theta plus sine squared theta plus cosine squared phi. This chunk, the cosine squared theta plus sine squared theta, is just going to be equal to 1. So on the interior, I'm left with sine squared phi plus cosine squared phi, which is also just equal to 1. So I get what I thought that I would get, that all of these sines and cosines cancel out, and we end up with just a rho squared. So at this point, I'm ready to set up my integral. We just decided that our bounds of integration, starting from the inside, my rhos are going from 0 to 2, my thetas are going from 0 to pi over 2, and my phis are going from 0 to pi over 2. My x squared plus y squared plus z squared just turns into a rho squared. I need to remember my red term of integration, which is rho squared sine of phi. And I integrate this d rho, d phi, d theta. So rho squared times rho squared just ends up being rho to the 4th. And when I integrate that with respect to rho, I'm treating sine of phi as a constant. And I end up with 1/5 rho to the 5th sine of phi, evaluated from rho equals 0 to 2. Of course, I have these outer integrals that get carried along. 2 to the 5th is 2, 4, 8, 16, 32 fifths. So I end up, I'll just put 32 fifths on the outside. Sine of phi, d. Oh, I interchanged the order here. It turns out it doesn't matter because the bounds were exactly the same, but let's just make sure that we have p's and then thetas. It really doesn't matter. I could have done it either way, but I do want to make sure that they match. So when I integrate this sine of phi with respect to phi, the integral of sine is negative cosine, so I get negative cosine phi evaluated from phi equals 0 to pi over 2. The cosine of 0, wait, maybe I should be a little less sloppy. I'm getting a little tired of doing all these integration problems. You will as well at some point, I'm sure. I'm going to come over here to finish off. So what are we doing right now? I'm going to evaluate the cosine of phi as phi goes from pi over 2 to 0. The cosine of pi over 2 is 0. So I get 0 minus the cosine of 0 is 1, and the negative of that becomes negative 1. Again, I still have my outer integral, that's my theta, that goes from 0 to pi over 2. I have my outer coefficient 32/5 d theta. So this is just the integral of 1. Theta goes from 0 to pi over 2 d theta. So I integrate this and I get theta. Let's not forget about my 32/5. And it looks like my final solution is going to be 32/5 times pi over 2. Again, the hard part was setting up the integration. The actual computation, my hope that I'm not making too many algebra errors. Thanks.